It is now time to start thinking about the solutions for non-homogeneous differential equations. So I'm just going to do a quick reminder. One form that the non-homogeneous differential equation can be written in is this. So we have our y double prime plus some function of x times y prime plus some function, again, of x times y. And then we have, let's say, g of x or f of x. I can never remember which one. It doesn't really matter. But the idea is we have a function on this side represented by g. Now, the acronym that we used when we had the homogeneous equation was HOLD. Now that it's a non-homogeneous equation, we're going to refer to equations like these, right? Whether or not the coefficients on this side are constants, we're going to refer to it as a NOLD, right? So for non-homogeneous, ordinary, linear differential equations, and again, here we're focusing on the second order, right? Now, if g of x happens to be identically equal to 0, then that leads us to the corresponding HOLD, right? The homogeneous case, right? So, we refer to this as like the associated homogeneous equation of the non-homogeneous equation. Associated because the left-hand side is identical. The big difference is whether you have a non-zero function in the NOLD case versus the zero function in the HOLD case. And if the coefficients are constants, we now have a way of solving. So I'm just going to say that, under certain conditions, so if we have constant coefficients, we know exactly how to write down the general solution. So it's so it's going to be C1 times Y1 plus C2 times Y2. And we know what's required for Y1 and Y2. These have to be two linearly independent solutions of the HOLD, right? So the question is, can we come up with something similar, right? To say, okay, this is what we need to be able to write down the general solution for the NOLD. And like when you look at both of them, again, because the left-hand side is pretty much the same, you would think that there is some relationship between this and this. And in fact, that's what we're going to establish in this video. What is the relationship between the general solution of this equation and the one that we want now? This is kind of our unknown problem that we're trying to solve. And we can see what little theory comes up, right? So, suppose, and since I'm using like little y1 and little y2 to represent solutions of the, not just solutions, but linearly independent solutions of the HOLD, I'm going to use big Y1 and big Y2. Suppose we had two solutions of the NOLD, right? So suppose Y1 and Y2. And let's go ahead and call this equation 1, and then I'm going to call the HOLD equation 2, right? Just for easy reference, right? So suppose we have big Y1, big Y2 that are solutions, right, to equation 1. Well, let's write down what that would mean. It would mean that if, for instance, I take my big Y1 and so let's see, so big Y1, and I differentiate it twice, and then I take P of X and multiply it by big Y1 prime, and then add to that Q of X times big Y1, no derivative there, right? And if I did this, I would get g of x, right? And then the same thing would be true for y2. Yeah, if I'm saying I have these two solutions that will satisfy my nullity, then it's the same. I would just basically just change these subscripts to 2. So y2 double prime plus p of x times y2 prime plus q of x times y2. That would also be equal to g of x, right? But look at what this means, right? So now, so if big Y1 and big Y2 separately satisfy the non-homogeneous equation, if I call this, since I already have 1 and 2, if I call this A and B, and look at what happens. If I take A and subtract B, right? I can basically look for like terms. Now, the interesting thing is the like terms would be whether you have like a P or a Q multiplying or not. So I can group these two. So if I take the top equation and subtract the bottom equation, I would have y1 double prime minus y2 double prime plus, and then I'll group the terms that have the p of x, and then that will give me y1 prime minus y2 prime, and group the terms that have a q of x, and that will give me y1 minus y2. But look at what happens now. Because both these functions, when I carry out these operations, they produce g of x. When I take the difference on the right-hand side, I will now have a 0. Now, because of our properties of derivatives, in particular, we have that difference rule of derivatives that says if you're taking the derivative of a sum, you can just take the that would be the sum rule. But if you're taking the derivative of a difference, you can take the difference of the derivatives. Same thing for repeated differentiation. So here, I can think of this as y1 minus y2 double prime, right? The derivative has properties that are similar to what we call linear transformations, right? Where if you're taking if you're finding the transformation of a difference, it's the same as taking the difference of the individual transformations, right? And this is our difference rule from Calc 1, and the same thing holds here, right? I can write this as y1 minus y2 prime, and then I don't have to do anything here. I have, because I don't have any derivatives, I have this. But what is interesting now is I started with two solutions to the nullity, right, to the non-homogeneous equation. But the difference of those two functions, look, they satisfy the holdie. So this implies that y1 minus y2 is a solution to equation 2, which is the holdie. That's pretty remarkable, right? Now, let's take it a step further. What does that mean? Well, we know every solution, right? This is what we did, and we did it, methodically as we went through all those three cases. We know that the solution to every solution of the homogeneous equation can be written as a linear combination of little y1 and little y2. So therefore, there exists C1, C2 in our set of real numbers such that this function, right, this difference that we just showed that satisfies the homogeneous equation, that can be written as c1 times little 1 plus c2 times little 2, right? But if we, what we're saying is, we're not saying that y1 and y2 are any specific functions. It's just we have a solution and another solution. So this expression here will work for any pair of functions that satisfy the non-homogeneous equation. So if we let let's say big yp be any solution to 1, and big Y, just so without any subscripts now, big Y be all solutions, and notice the qualifiers here. Y sub p is any solution to the nullity, and big Y with no subscripts be all solutions of the of 1. Then the same relationship has to hold, right? Because what we proved earlier is that for any of them this will work. So I have all, and then I'm subtracting a specific one. So y minus yp must still be equal to, again, some linear combination of little y1 and little y2. Again, little y1 and little y2 represent the functions that make up the fundamental set, or the basis for the associated homogeneous equation, right? So why is this important? Well, it now gives us essentially a procedure for figuring out all the solutions for the whole-D. In other words, the general solution of the null-D. Did I say whole-D? I meant null-D, right? The non-homogeneous equation. So therefore, big Y can be written as, and let me write it like this, C1 Y1 plus C2 Y2, and then now add this special function here to the right, and then we have so this gives us all the solutions of the non-homogeneous equation, right? So this part here, it is often denoted y sub c. So I'll write it like this. And now that we've sort of gotten to the result that we need, I'm gonna stop distinguishing between big Y and little y, and I'm just gonna call this Y. But this Y now represents the general solution of the non-homogeneous equation, and then I'm just gonna call this again Y sub p. Y sub c is referred to as the complementary function. So complementary, maybe it gives you a lot of compliments. No, it's a helping function. It's a part of the solution, and then this is called the particular function or particular solution, right? And what we have here is that the sum of these two functions give us, so when we add them together, we are going to get the general solution of in fact, let me write it now, of the null-D, right? Right. And this is another version of the superposition principle, but this is the superposition principle for non-homogeneous linear differential equations. All right, so let's state the theorem. Right, and I know that the argument seems a little circular, but it gives us what we want. So let's say here's our theorem, and this is the superposition position principal for, and I'll just use our acronym NOLDs, right? Again, this is the second order version, and let's write it down. So the general solution of our y double prime plus p of x y prime plus q of x y equals, let's say we have f of x, right, is given by y equals, and this is why I just switched back to little y, because our differential equation now is using little y as our dependent variable. So that general solution, right, is given by, I'll just write it like this, y sub c plus y sub p, where y sub c is the general solution of the corresponding whole-d, or associated whole-d. So that's when we essentially solve it with a 0 on the right-hand side. And again, we know how to do that for all cases. And y sub p is any particular solution. So this is where we're going to have to figure out, how do we find this y sub p? So any particular solution of the null-d, right? So of the null-d. So there we go. So this is our second superposition theorem, and it tells us now how do we go about finding the general solution of one of our differential equations when we don't have a 0 on the right hand side. And it's a two-step process, right? Now, to kind of wrap up this video, what I'm going to say, it might not be clear right now how to find y sub p, right? So I'll just say this. So right now, it might not be clear well, let's say it this way. Yeah, might be clear on how to find, or as to how to find y sub p, but there are two methods, right, that we will use to do so. And here are the two methods. So this is just kind of a preview of what's coming up. The first method is the method of undetermined coefficients. Right? And then the second is the variation of parameters. And this is what I will say. They both involve algebra, right? And they both involve calculus to varying degrees. You will end up using more calculus in the variation of parameters method as opposed to the method of undetermined coefficients. So and they both have their pros and cons, which we will look at as we go through the details. But our big goal now is establishing this particular theorem. So now that we have this in mind, maybe we should jump right into one of our methods for finding y sub p. And I'll see you to do that in the next video.